So from the formulas, the reason why I like to go over the formulas is because we can see that two things are going to determine how big or how small your interval size is. The first thing, which was what we just discussed, is how much sampling error you have around the mean, right? Your SEM or S sub x bar. The bigger your sampling error, the bigger your interval becomes. The second is the degree of confidence we choose. Remember, we could choose 68, 95, 99. Those are by convention. And as the degree of confidence goes up, the interval size must get bigger. We want that better and better chance of actually capturing mu, or the fish. All right. Now, what if it's the case that sigma is unknown, which, we've been working with, right? We said that's okay. We're just going to estimate SEM. But what if you have an N less than 30? So you have a small sample size. What are you going to do? Well, you've already learned about what to do when you have a small sample size. You use a different letter of the alphabet. You're going to use T instead of Z. Notice how I changed the way I pronounce the letter just to make it rhyme. So use T instead of Z. Formula looks identical except for that switcheroo here. All right, so we put the letter T here, and it would be a good idea to review T distributions. So that was in the chapter on Z scores. We also talked about T scores. But except for, and I'm going to, say a few things about them too. I'll do that here. But other than switching, Z and T, everything else remains the same. Now, here's pop quiz for you. All right. If you used T instead of Z, would the interval be bigger or smaller, and why? What do you think? What do you remember about T versus Z? You might remember that if you are going out into the into the tails, T has fatter tails. F-A-T-T-E-R, fatter tails. And you're going to see in a second, but what that means is your T, whatever this number equals, it's actually going to be bigger than what Z would equal. And if the T is a bigger number, what is that going to do to the size of the interval? It's going to increase the interval. So the short answer is if you have a sample size less than 30 and you use T instead of Z, your confidence interval, that interval size will be bigger than had you used the Z. All right? Probably want to write that down, but let me show you the explanation. Then maybe you're just going to be able to remember it because it'll make sense. So this diagram should look somewhat familiar. It's the same one I used in chapter 5 on Z-scores. So the blue line is meant to represent the Z-score distribution. And remember, there's only one of these. If we talk about the Z-score distribution, that means we have plotted every possible Z-score, past, present, and future, universe, and beyond. So there's only one of them. But you may recall that T distributions, represented here by a red and a green line, these T distributions, there's actually an infinite number of T distributions. One for every degree of freedom, which is pretty much like saying one for every sample size. Now, I have not drawn an infinite number of T distributions. I've only drawn 2. What we can say about how T and Z, how these distributions compare, is that Well, first of all, if we have a sample size greater than 30, you won't actually see the difference. T and Z become virtually indistinguishable to the naked eye for these larger sample sizes. So in that case, it doesn't really matter if we're using Z or T, whatever we want to call it, because they look identical. The numbers will be the same. But for smaller sample sizes, what happens is that T becomes more platykurtic compared to Z. That means flatter, right? Flatter than normal. So when you push down on T, remember the analogy of the balloon? When you push down on these T distributions, the air's got to go somewhere in the balloon. So if this were a balloon and you're pushing down, where does the air go to? Into the tails. Let me show you over here, because then you're not being distracted by all that. So you see how these T's, the red and the green, they have fatter tails compared to Z. So if we were to look at the area under the curve here for Z, so just look at this area, okay, and come up with a number. Well, let's say that's, I don't know, 15% of the curve. I don't know that it is, I'm making it up. But let's say it's 15%, okay? Well, if we were to look at T's, the green and the red, notice how it goes above that, above Z. So we're adding all this extra area here. So now, whereas this area under the blue line was 15%, 1.5, now the total area under the curve, if you look under the T's, that total area might be closer to 20%. The T distributions will have fatter tails compared to Z. All right, and that's true when you have those small sample sizes under 30. So what? Well, why do we care? Remember that the goal of a confidence interval, ultimately, we want a high confidence interval. We want that probability to be as high as possible. So even 99 in that respect would be better than 95, right? Because you have 99 chances out of 100 that the interval will include mu versus 95 times out of 100 that the interval will include mu. So, ideally we would want it to be 99, all right? But the other goal of a confidence interval is to keep the interval size as small as possible. So that's the range from the lower to the upper limit. We don't want that range of values to be very large. So if we had that large sample size of 30 or more, we could use Z in the formula. All right. Now, for the 95, remember that the Z score is 1.96. Now, also remember that the total area under the curve between plus and minus 1.96, that middle portion here, that's 95%. Well, if this is 95 in the middle, that means we have 5% left over, right? Because it has to sum to 100%. So if this is 95% here, that means with the 5% left over, 2.5% are going to be in this tail, and 2.5% are going to be in this tail. All right? So again, we're using the 95% confidence interval. Z is 1.96. And then whatever this is here, that's going to be 2.5% on this side. And then I don't have the actual Z score marked here, but it would be 2.5% on that side. Now that's if you're using Z. But now let's say you have a small sample. So we have less than 30 in the sample. We're going to be forced to use T. But if we look at the total area under the T, so pick the red or the green here, they kind of merge, so it doesn't really matter. But if we looked at the total area beyond a T of 1.96, so pretend this is your T, is that still 2.5%? No, it's greater, right? So if we use T 1.96, we would not be using the 95% confidence interval. because to use the 95% confidence interval, we have to have 2.5% in the tails. So we're going to have to, instead of using 1.96 as our t-value, we're going to have to move over until we get to a t-value where anything beyond that is 2.5%. All right, so you see how our t-value needs to be a larger number? Because remember, we start with 0 here in the middle of the distribution. And as we go along the x-axis, the numbers are getting bigger and bigger and bigger and bigger in the positive direction. Here, if we go in this direction, they're getting bigger, 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 but just in the negative direction. So if we were using a t-score and the t-score was 1.96, we would have more than 2.5% in the tail. So we have to move along the x-axis and stop, and the place where we stop has to be the value of t, where anything beyond it, this area here, is now 2.5%. Okay? Now, I just made up 2.66. I don't know if it's 2.66. Sounds good to me. I would need to know degrees of freedom in order for me to know what this number is exactly. Okay? But the point is, you can see that your t value is going to have to be bigger than the z value for the same confidence interval. All right? So if you want the 95% and you're using t, inevitably, you're going to get a larger t-value. And what is that going to do to your confidence interval? It's going to increase the size of the confidence interval. From the lower limit to the upper limit now is going to be expanded. So researchers really try to get samples of 30 or greater because they know if they're using anything less than 30, SPSS will default to a T, and that's going to increase the size of the confidence interval, and we're going to lose precision. All right? So that's the, I kind of prepped you a little bit for this when we were talking about z-scores and t-scores in the previous chapter, and I said, we want to use z or z, we don't want to use t, and I couldn't tell you why. Now I'm telling you why. Okay, so we are using t. Again, the formula is identical except we put the letter t here. The primary difference, though, is that you're going to have to look up this t value. With z, you have these memorized. If you want the 95% confidence interval, you use 1.96. If you want the 99% confidence interval, you use, 2.58. But for t, you need a t table or an app, and you're going to need to know the degrees of freedom, and then you get this number. But after that, everything is the same. So, book is to refresh your memory and further enhance learning, hopefully. If we use the 99% confidence interval, and this is going to be true, all these questions actually are true whether you're using T or Z, okay? If we use the 99% confidence interval, will the interval range be larger or smaller than a 95? Well, it's going to be larger. Where is it? Larger, right? Because if we want a greater chance of mu being in the interval, we're going to need a bigger net. We're going to need a larger range of values to increase the probability of being right. Okay, and again, that's true for T and Z. You're going to come to the same conclusion. All right, how about this one? How does the amount of sampling error affect the size of the interval range? Again, with more sampling error, there's more uncertainty. You better use the larger net. All right, so if we have more sampling error, it means that the interval size is going to be larger. We need a greater range of values to make up for that uncertainty. And it's the same for t and z. And then the last one, how does the value of the mean affect the size of the interval range? Think about that for a second. The value of the mean. So does it matter if the mean is 10, 20, 30, 40? Does that affect the size of the interval, right? The range, the actual range of values. That is, whether the spread is 10 points, 15 points, does it affect the interval size? The answer is, it doesn't. All the mean does, besides sitting in the middle of the interval, right? X bar is always in the middle. All it does is it gives you a reference point. Remember that what you're going to do is you're going to look at your sample mean and then you're going to add and subtract this product. It doesn't affect the size of the product that you add and subtract. All right? How much you add and subtract from X bar tells you how big your interval size is going to be. Your interval size is determined by how much sampling area you have and the actual value for t or z, depending on which one you're using. Remember, there's only two things that affect the size of the confidence interval. All right? So it's the sampling error, right? How much sampling error you have, and the value of t or z. And the value of t or z is going to depend, well, do you want the 68% confidence interval, the 95, or the 99? That's going to help determine what this number is. Okay? That affects the size of your interval. X bar is just your reference point. Okay? It's what you add and subtract to and from in order to get the upper and lower limits. But the size of the interval, the number of points in between, is made up of this product. Okay?